Imagine standing on the edge of a deep valley in ancient Gaul. Before you is a massive gorge, hundreds of feet deep and a mile wide. Behind you is a stone channel carrying millions of gallons of fresh water from a mountain spring miles away. Your job is to get that water across the gorge and up to the top of the opposite hill where a thriving Roman city is waiting. You have no electric pumps, no diesel engines, no steel pipes, no modern machinery of any kind. If you try to build a stone bridge straight across, the structure will have to be higher than a 40-story building. It will collapse under its own weight before you even finish the first row of arches. And yet, if you look across to the top of that distant hill, the water isn't stopping. It's rushing up the slope, defying gravity and pouring into the city. To anyone watching 2,000 years ago, it looked like absolute magic. It looked as though Roman engineers had found a way to make rivers run backward. So how did they actually do it? How did the ancient Romans move millions of gallons of water uphill without a single modern machine? To understand this, you first have to understand the core rule of Roman engineering. The Romans didn't have pumps, but they had gravity. Every famous aqueduct you've ever seen, those massive, elegant stone arches stretching across the countryside, was fundamentally just a slide for water. The entire system was built on a continuous, silent, downward slope. Roman surveyors used an instrument called a chorobates, a 20-foot-long wooden bench with water channels and plumb lines to measure the terrain with terrifying precision. They engineered channels with gradients as shallow as 1 foot of drop for every 1,000 feet of distance. Over a course of 50 miles, the water was constantly, silently falling. Most of the time, keeping that downward slope was simple enough. If a small hill was in the way, they dug a tunnel through it. If a shallow valley appeared, they built a stone arcade, a bridge with arches, to keep the water elevated on its gentle slope. But every now and then, the landscape presented a total nightmare. A massive, plunging valley, a canyon hundreds of feet deep. Building a bridge across a small valley was easy. Building a stone bridge 200 feet high across a massive gorge was impossible with ancient materials. The stone would crush itself. If they tried to wrap the channel around the contours of the valley, the distance would add miles to the journey, losing the precious elevation slope entirely. If the channel got too flat, the water stopped moving. If it stopped moving, the city above went dry. So the Romans turned to basic physics and harnessed the phenomenon that modern engineers call the inverted siphon. Here is how the trick works. Instead of keeping the water open to the air on top of a bridge, the Romans funneled the open channel into a sealed, airtight header tank at the edge of the cliff. From that header tank, the water was forced into a network of heavy, thick pipes. These pipes ran straight down the steep wall of the valley, plummeted across the valley floor, and then headed straight back up the cliff on the opposite side, emptying into a receiving tank. Now ask yourself, how does the water get back up that second cliff? It boils down to a fundamental law of fluid dynamics. Water in a closed, connected system will always seek its original level. Think of a simple U-shaped tube filled with water. If you pour water into the left side, the weight of that water pushes down. That downward force creates massive hydrostatic pressure at the bottom of the bend. That pressure has only one place to go. It forces the liquid up the right side until the water level on both sides is identical. The Romans realized that as long as the starting tank on the high cliff was slightly higher than the receiving tank on the opposite cliff, the weight of the water falling down the first slope would generate enough immense pressure at the bottom to literally blast the water up the other side. It wasn't defying gravity. Gravity was pushing it down so hard on one end that it had no choice but to climb the hill on the other. It was an engineering marvel. But executing it in the ancient world was a living nightmare. The physical forces inside an inverted siphon are violent. As water plunges hundreds of feet down a valley wall, the pressure builds exponentially. At the bottom of a deep valley, the internal pressure inside the pipes could easily exceed 150 pounds per square inch. If you make those pipes out of standard Roman pottery or clay, they will instantly explode into fine dust under that pressure. So, what did the Romans use? Lead. Roman blacksmiths hammered out huge sheets of solid lead, wrapped them around wooden forms, and soldered the seams shut with molten metal. Because a single massive lead pipe would burst under intense pressure, they split the water flow into multiple parallel pipes, sometimes up to 12 side-by-side lead lines to distribute the force. For a single siphon, like the famous GR aqueducts serving the city of Lugdunum, modern-day Lyon, the Romans used over 10,000 tons of solid lead. Mining, smelting, transporting, and soldering that much lead across an entire empire was one of the largest industrial operations in human history. And even if the lead held, the water itself posed a deadly structural threat. When thousands of gallons of high-pressure water hit the bottom of a valley and suddenly change direction to start moving upward, it creates a terrifying force known as a hydraulic shockwave or water hammer. If that rushing mass of water hits a sharp turn, the kinetic energy will literally tear the pipes out of the ground and smash the masonry work to pieces. To stop their own aqueducts from ripping themselves apart, Roman engineers built massive, heavy stone foundations at the bottom of the valleys to anchor the elbow bends. They also constructed lower bridge arcades across the very bottom of the gorge. They didn't build a bridge all the way to the top, they built a smaller bridge halfway down, just high enough to flatten out the sharp curve at the bottom and reduce the maximum pressure inside the pipes. And then there was the problem of trapped air. If air pockets got trapped inside the heavy-pressure lead pipes, the compressed air would block the flow of water or cause explosive pressure spikes. To solve this, Roman technicians installed open-air relief shafts or blowholes along the upper slopes to let trapped air escape without bursting the line. When everything was aligned, the pipe thickness, the joint welds, the anchor stones, the elevation gradient, the system worked flawlessly. Water would plunge down into the dark abyss of a valley, roar across a stone bridge at the bottom under immense pressure, and then climb straight up the opposite cliff face, erupting into a stone tank high above, ready to flow into the public baths, fountains, and homes of the city. Without electric motors, without fuel, and without computer simulations, the Romans used pure geometry and physical force to push millions of gallons of water up mountain walls. They didn't break the laws of physics, they mastered them so completely that to anyone standing at the top of the hill, it looked like the earth itself was bending to the will of Rome.